So this is the general lecture on the Paleoseismology of reverse faulting, and so it is more of a survey as opposed to what I just did, which was just specific review of the single earthquake. So I'll talk briefly about the classes of terrestrial contractional deformation zones, then historic earthquakes, what we learned from them, discuss a little bit about segmentation. Reverse faulting is also really about folding, coseismic folding, and then we'll discuss some trench examples. So from Yates et al., from the earthquake geology textbook, they identify 4 main places where we see reverse faults. So active fold and thrust belts and that are at plate boundaries. So the Himalayan front is an example, or North Africa in the Atlas, or in the Middle East, or in Southern Europe. So back arc fold and thrust belt. So this is what you have here in Java, right? If you go on the north side of the arc, it's a fold and thrust belt. We don't know how active it is, but and then reverse fault range is associated with major strike slip faults. So this is if you have big bands in strike slip faults, like the San Andreas fault has one called the Big Bend. There are reverse faults around it that are significant, and also there are some along the North Anatolian fault. I think the Great Sumatran fault doesn't have many big bends. It has some big stepovers that make it more like it could have big normal faulting earthquakes in the stepovers, but it doesn't have the big contractional bands. And then in continental interiors, if you remember from my early lecture about the world stress map, most continental interiors are in compression. And so we expect most earthquakes in stable continental interiors to be reverse faulting ones. So if you look in Australia, the earthquakes in the middle of Australia are reverse. And so, yeah. So here's just, as usual, we learn a lot from historic earthquakes. And so I just showed you one studied from 1911 but I'll just keep going. So here's Chichi. I showed this slide before, so I'm going to go kind of quickly past it, but there's a few more pictures here just showing the different kinds of fault scarps that formed in Chichi. And so this is why we study the historic events, is to get our mind ready to anticipate what we'd see paleoseismologically. So you can see the material types like this track and the grass, because they have some strength, and the rupture doesn't necessarily tear it. It's like carpet that just folds up. And so this makes for a very complex initial shape that once, let's say we bury it, we try to find a buried earthquake that looked like this, we have to have this in our mind when we look at the trenches. But you can also have more just standard scarp with colluviation like these, so more high angle features. And so this, as I was saying in my sketch before for Chan Kimin, the thrust faults usually have the most complex shallow geometry, and so they make for fairly complex and distributed deformation. So here are some examples from Chichi. So there's one uplift and bulldozing. Here's the main thrust coming up, but then a back thrust. And then here's coming up with a little rollover, and so there's normal faulting here. So this could be the example I had from Chan Kimin. Here's one where there's kind of this little pop-up right at the fault. And then here's maybe the simplest example with just a more steep thrust and then failure of the nose of the scarp. And so the point of this paper was first to show this distributed deformation for geology, but it turns out it's also a problem for ground deformation hazard for houses and structures. So for example, in the Pakistan earthquake and the Kashmir earthquake, the rupture went through a lot of villages. And a lot of times if the village was on a hill like this, it was completely destroyed because the whole hill was deformed, and also there was strong shaking because it was in the near field of the earthquake. But the ground was completely deformed, and so the damage was really severe. So that's an important thing to be aware of. So here's another example of famous reverse faulting earthquake. This was the Telas Nom. So I talked about this in my introductory remarks, where there was the main rupture zone like this. Here's the scale. But it was a kind of an oblique sort of sinistral reverse. And so there was some important extensional structures associated with it. And so that's what this showed, was these, in the hanging wall, things were showing really dramatic normal faulting, but clearly secondary. And here was the other one. This is showing that shearing of the hanging wall. So they're more en echelon, small grabens. And then the other thing I said about Telas Nom was that it had another dam situation. So it uplifted, and basically this river was stopped because you see the uplift was 4 meters. So it was enough to dam the river by at least 4 meters. So this lake formed. And so then there was paleoseismic work done that showed that this seemed to happen about every 1,000 years. There was a inundation of this basin. So that was the way that they did the paleoseismology, was looking at the formation of the lakes. So that, of course, assumes that each earthquake is about the same size, and so it can cause the damming and has to be, several meters vertical. So this indirect evidence from the lake wouldn't show if there was small earthquakes on this fault, because they might not cause the damming, but big earthquakes will cause the dam. And so anyway, questions about Telas Nom? This one's in North Africa, Algeria. So, okay, so here's just some more characteristics of fault scarps from reverse faults. So here you see is the overhang. So it's not a very big offset, but there is the fault surface itself. But because of the overhang and the weak material, it usually slumps immediately. But you get a sense for the complexity of the initial form. And so now if we see this paleoseismically, we have to have it in our mind. This was some evidence from the Kashmir earthquake, and just because for the other kinds of faults, I had showed these same slip curves. So this is distance versus vertical separation, so some kind of vertical offset. And what you can see, and what their point was, that it's 60 kilometers long, but has as much as 7 meters of offset. So it's a little bit high slip length ratio. Because if you think like Denali, remember Denali was 330 and it had peak slip of 7. So this is 5 times shorter, but still has large slip. So maybe distinctive for some reverse faulting events is they have high slip. And so it's thought that sometimes this means that the stress drop is higher. So the earthquake had more energy stored up, and when it released it, it put that much more slip out. The other thing that they show here are these little dots, which are offset on some terraces, and they're low relative to the nearby offsets. And so they interpret this as showing distributed deformation in the gravels on the fluvial terraces. So, and then when they draw the interpretation of the slip distribution, you see this gray boundary they call the 2-kilometer interval envelope. So they're basically taking the sort of average along and basically taking the maximum, not counting for the error. So any questions? Okay, so just keeping going. So there was an earthquake 1988 in Armenia that was fairly well studied by this French team, and Philippe et al. And so one thing they did is they made this really very nice little block diagram of the styles of reverse fault scarps that they saw. So some were simple, just kind of a steep one, but it had a little cracking on top, to more of these kind we saw in Taiwan, where it's just like a carpet that's folded. So I always like this diagram because it's kind of a nice summary of these forms. So one thing that, as I said earlier, is that thrust faults are so segmented, or reverse faults tend to be quite segmented when they occur, and so they violate a lot of our usual rules. So as I showed for the Kebin earthquake, it broke through that 10-kilometer step over. This is a paper from 1996 from Charlie Reuben, and he argues that a lot of times we underestimate the potential magnitude of reverse faulting earthquakes because we overly segment the rupture in terms of our expectation. So, here, look at this one. The scale for all these is 5 kilometers here. So this Japanese earthquake was really discontinuous, and this huge gap, like almost 10 kilometers between rupture zones. So if we looked in the past, paleoseismically, we'd say, well, these were probably two different earthquakes because they're so separated, even if we knew they're about the same time. Telas Nom, you see, is quite irregular. This Tehachapi earthquake went blind for maybe 10 kilometers. So it was breaking the surface, and then it went down under the ground, and then it looks like it came back up here on this end. So unexpected connection. And then look at this huge Chinese earthquake. We might expect these kind of boundaries to be step overs that might or might not stop the earthquake, but definitely something like this or this, we wouldn't expect them to break together by our usual sort of segmentation. So this is an important lesson that, Charlie was trying to remind us of in this paper, and we see again and again for reverse faults. So in a way, you could say the segmentation I've talked about before applies better for normal faults and strike slip, and reverse almost follow their own rules. So I know we have our mountain front activity class guys here. So here's an example of mountain front segmentation using geomorphic indices from Bull. He's one of the kind of gurus of this. And so he looked at a number of different indices along this reverse fault system. And so they were range front sinuosity, valley depth, width ratio, and faceted spurs. So remember you asking about faceted spurs on reverse faults. So in this place, there are a few, even though we said that they don't usually form that well. And so what he could show is that, he mapped the different classes, and in general, this end of this San Gabriel Mountains looks like the faults are more active. And then it goes through a zone that's less active, and then it gets more active again. So this is in this case, especially because it's a thrust, most of these kinds of indices are better indicative of differential rock uplift rates all across fault zones. So comments? So this diagram just reminds me that there's lots of folding associated with reverse faulting, and I've already showed this some, but these, basically just a regular thrust, or does it have some kind of ramp to flat transition that produces some folding above? And here's just another diagram from Burbank and Anderson, where we have a ramp flat transition, and so the fault's not even breaking the surface, but it's causing this tilting. And then if you have steady sedimentation over the thrust front, you'll see this kind of difference in thickness on either side of this, they call the growth section. And one thing they argue is that perhaps these abrupt changes in thickness are associated with individual earthquakes that are causing the tilting. So they take, for example, some inferred uplift over the ramp and convert that to slip on the ramp. So this is a important kind of way of thinking about reverse fault systems. And so here's just some views. Here's a thrust that goes across some terraces. And so you can see it bifurcates. And also you can see that the lower terraces, which are younger, have smaller scarps than the old ones, as you might expect. So this old terrace has more offset than the young one. And so down here at T5, this last scarp, maybe it's the last earthquake. You see it's very short, but then as we go along here, we're basically getting older features that are offset, so more cumulative deformation. And so this is from China. This is a place where you can see the bedding here shows that it's a fold. And in this case, the folding is every time the slip occurs, there's bedding parallel slip. And so what they showed is there's lots of little faults that move during these earthquakes at the surface. So these flexural slip faults are the ones that are leaving the record of ground deformation that we might trench. And the main fault is blind. It's down underneath here somewhere. So if we go, for example, back to here, it would say that hard to see, but some of these, if you made this steeper so that the front of the fold was almost vertical, then the bedding can slip. And that's what this is trying to show here. So, and these guys, when they work on this earthquake paleoseismology in China, at this place, they'll trench these little fault scarps, and they'll try to at least get the timing of the paleo earthquakes, but they definitely can't get the magnitude because it's secondary slip, so it's very difficult to say what the main slip was. Questions? So here now a little bit on reverse fault scarp paleoseismology. So as I've showed already, these, here's the pre-faulting case, here's the earthquake, and the fault tip kind of goes up, and material's pushed over, and we get this sort of rotated condition. Here, then we erode this material and deposit it in front. Keep going. There's two earthquakes. Here they show injected, but the other thing you can see is this cutoff, and I showed this in our trench from the Palmyras before, where in the earthquake this tip kind of rolls over, but the next earthquake tends to cut it off, so it leaves the old fault surface part of it behind, and then it cuts it off, and then it'll cut it off again and again. So we get these kind of noses are left there, and then it keeps cutting the back off of each nose. And so then here would be the complex sort of paleoseismology that we'd have to interpret. And you'd have these little wedges, 1, 2, 3, 4, we try to date. And here they're steep, here they're a bit more gentle. So here's the deformation just from Chi-Chi. So this is, we know what happened. And this just shows what happens when you have these superficial materials that have a lot of cohesion, and also they can flow and they kind of detach. So you get basically this big mound that formed during the earthquake with cracking and this kind of strange fold at the surface, but at its depth, you see it's much simpler. It's just a basic reverse fault cutting the gravels, but the superficial materials have a very different mechanical property, and so they just pile up. So they dug this up, and then they tried to retro-deform it. So remember I talked about retro-deformation as a way to kind of put everything back together. So they tried to measure the offset and opening on every one of these little faults, and then they tried to slide it all back. And so this is what they came up with, was that, you know, like this fault here ends up being this one. So it was possible to you know, rebuild it, and it took, you know, at least 3 meters of shortening to do it. So I just wanted to, as I said before, I'll try to say each time this idea of retro-deformation as a key strategy for any paleoseismic project is, can you undo what happened in the earthquake? So questions? So here's a huge offset from the Himalayan front. So this is the Himalayas. And for many years, they didn't know what the paleoseismology was. No one had really tackled paleoseismology in India on the main frontal thrust. But they started doing it about 15 years ago. And so this site is right here on the front. And because sometimes people thought, well, maybe it's blind, like if there's big earthquakes on the main frontal thrust, they, you know, they're just deep and they might be very distributed, so we'd have a hard time, you know, really interpreting them. But here they found this is, I'm not sure if this is I think this is a river cut. No, I guess they have some natural exposures and then some trenches that were dug, but they're very big because the offsets are quite large in some of these earthquakes. It might be 17 meters in one earthquake, which is what you expect. It's like a subduction zone on land, right? This is look at the size of the interface is like 100-kilometer width. And then the, you know, distance along the Himalayas is like 1,000 or more kilometers, right? So these are big earthquakes, and there's some historic precedent that there were magnitude 8s in the early, like 1905 and 1930s. And so the idea is that there are M8 events. And so these paleoseismic studies like this one were able to show cumulative, you know, large offsets. And but the problem was just almost logistical. If you want to measure 17 meters in a trench, you need to have at least 17 meters of exposure. So you have to dig huge trenches to study these earthquakes. So I'm just going through many examples now, so you have to stop me if it's confusing. So now back to a small reverse fault and maybe oblique slip. And so here you can see this shear zone. It's really narrow, but here you can see, you know, one event that got buried, second event buried, and this one cuts off those layers, but then it was buried. But notice how it's also getting kind of vertical here, and even this feature here is kind of being driven into the fault zone. So this is a really compact reverse fault zone that's probably oblique slip. It's probably dextral reverse. And one way we can see that is some of these higher angle features in the middle here help us to get a sense of that. Dextral shearing that's in there. So this you can see is in some ways is not a very good site to do paleoseismology because it's so complex. But on the side here we have a pretty simple story. We can interpret at least part of the record easily. So this is a good unconformity and a good one there. But then up here it's more complicated. There's a landslide that's coming in, and this seems pretty challenging site. So here's one, and this one I wanted to show because it's a combination of a trench with borings. So see these lines here, are large diameter boreholes. So remember, I said that you can, for construction, they have these tools which you can get a meter diameter borehole, and then somebody goes in a cage down in there, usually the graduate student. So this guy, he was the student, and this was the professor. So the student goes down. I'm just joking, but because it's a little scary. I'm not sure I would do it, but yeah, Gayatri could go down, and so it's safe though. You know, there's rules about this, and if the material's too weak, you don't do it. But you can see they can drill 20 kilometers or 20 meters deep, and then you go down in this little cage, and you can describe the layers as you go. And so what they could do is they could find the fault as this sheared clay zone. And then another one here, okay, we see the fault. And then, there's the fault in the trench. And so they combine the large diameter boring with the trenching. And so this is a good strategy. And Dolan, he's kind of an expert of this kind of approach. But large diameter bores give us good context. So you can go deeper, and he might do some further away on either side. So that's this one. Here's just back to another one of these cartoons that's showing a little bit more of how this might look. We have one earthquake occurs, and just like in our examples from yesterday when we did the fault scarp and the normal faults, you can get this colluvial wedge to form. But here, if the material is the right mechanical behavior, it's kind of brittle. It'll fail, and it'll almost look like a normal fault scarp. It's just a steep scarp. We don't really know the sense of motion unless we trench it. And then here you could do diffusion modeling of this one. And so we go through here's another earthquake. Colluvium comes in, gets steep initial form, and then here it's diffusive. It has that nice anti-symmetric sort of, convex concave form. So usually I argue against trying to do diffusion modeling of reverse fault scarps because there's so much folding that it looks like it's erosional rounding, but it's actually the primary warping, and so it's difficult to tell the two apart. But this sketch, if this condition could be observed in the field, then you maybe could try diffusion modeling of reverse fault scarps. So here's another one. This is, I would say, I call this kind of an ugly one. It's, you see it's kind of maybe almost, again, it's pretty steep. If it's reverse faulting, it's very steep. And you see right at the surface, the faults all kind of lay over. So we get this very complex set of relationships in the shallow area with this hanging wall collapse. And then down here below, we get this complex colluvium with blocks that are falling in front of the scarp. So this is from Washington State, so a humid environment. Here's a Chichi earthquake, and just showing this kind of low angle sort of thrust, with some of the thrusts actually going blind into the bedding, and then this overturned fold right in the nose here. So we have this overturned bedding below, and here's the interpretation of it. And so the other thing you can see is, this nice, fairly objective log, and then they have their kind of more interpretive log afterwards. So then finally, this is Himalayan, another one, Himalayan thrust front. So again, showing this kind of the nose of the hanging wall just driven out into the topography in front, and then their efforts to try to date it. So they, I think, would put the earthquake, obviously it breaks through here, and these layers somewhere about here is post-earthquake, like this colluvium. So they can date the colluvium at 1436, but then somewhere around here, 1306, or here, they're for sure older than the earthquake, right? So, and then these guys are older, so they can, and you could build a ox-cow model of this to figure out the timing of the earthquake. But it looks fairly well constrained, because 1436 to 1257 for sure, and maybe I don't know if they consider this pre or post layer. So this is the final slide of this lecture. It's a attempt to just classify different characteristics of the reverse faulting environments, where you have, on this axis kind of more brittle, narrow, single fault to ductile and folding. And this is the increasing width. So this would be a distributed faulting environment, and then this side would be a really big open fold. And so then they depending on, so for example, with the big folds, we may not see so much of the colluvium. We would just see onlapping sedimentation of the fold. And so we'd have an unconformity there. Whereas the colluvial wedges are more for narrower width environments. And then the collapsed tip are these small ones, like, remember I showed the San Fernando, one of the early pictures. So this I thought was a helpful diagram to sort of put different sites on our discussion. So Telas Nom EA, that's here. It's really open folding. Okay, so I think that's the end of that lecture. Reverse faults, let's see. Yeah. So let's take a 5-minute break and we'll do our next lecture. Okay?